Hello there, CodeMaker4 here. In this video I'll be teaching you how to program the SMC1. SMC1 is the acronym for Scrap Mechanical Computer 1. It's the first series of computers I have made, and the showcase of the original version is also the first video on my channel, by far the best video on my channel, or not best, but at least most popular, most viewed. Right, so before you can program the SMC1, you of course need to know how to do that, so this is going to be a tutorial for that. I already had a tutorial in the original version, but it was kind of crappy, so I'm just going to be redoing that here. I've already released a 1.1 version, so we're going to quickly discuss the differences. Programs are completely cross-compatible, so if you write a program for one, it will also work on the other. They both have 31 programming lines and 16 bytes of RAM, but the way the RAM is stored is the main difference. It's because the 1.0 version, or original version, uses switches, which are slow but easy to debug and read and write by humans. And SSC 1.1 actually uses delatch gates, which makes the entire computer about 25% faster, but it's way more difficult to actually read and write to by a programmer. So because it's easier to actually make a program on the 1.0 version and afterwards run it on the 1.1 version because that's faster, we're just going to be making a program tutorial for the 1.0 version. So let's look at a bit of this programming line. So completely on the left we have the weird black and white pattern. So that's actually a binary pattern, and it indicates what line of code is actually written on that specific part of the programming card. It's a program index, and you don't edit it. If you edit it, the computer will have trouble actually knowing what line of code it's currently reading, which will cause the program card to actually be unreadable. Right to the right of that we have the yellow part, which is the if statement. If you simply leave it as is, the actual instruction will always be executed. But if you paint specific blocks white, you can actually make sure that the specific line is actually only executed when the statement is true. What those A and B values are going to become clear later. The green part is the RAM address for writing, and it determines what address you want to write on that program line. So say you want to write something to address 5, you simply put binary 5 there. Of course the green is going to be the least significant bit for that. The blue line actually is all about what you're going to be writing on the green address. So the blue part can be a RAM address to read from, or a constant value. So say you want to simply write a 3 there, you can simply put a 3 there. If you want to actually read from address 3, you also need to put a 3 there. Of course, the computer will have no way of knowing this, so in between those lines there's a purple line, which determines if the blue part is actually a constant value or a RAM address. If you leave it as is, it will be read as a constant value, so it will be literally writing whatever is on the blue part. But if you paint the purple part white, it will be actually first copying from the RAM address specified in the blue part. I hope that's clear. So as you may have noticed, there's no way to actually put the add instruction in here. A instruction to add numbers, or to jump to a specific line of code, or to take user input. And that's actually where the weird part of the computer comes in. Because what I've done is I've hardwired some of the parts of the computer to the memory. So, for example, the ALU input A is simply address 0, and if you want to change the ALU input A, you simply change address 0. ALU input B is address 1, and the sum of those will automatically be put in address 2. So, say you want to add 3 and 5 together. We put a 3 in address 0 and a 5 in address 1, and the output 8 will automatically for us be put in address 2 to do stuff with later. If you want to edit the program counter, which determines what line of code is actually being execute it, or in other words, jump to this other line of code, you simply edit address 3. Address 4 is the user inputs, that's the switches the user can interact with, and the user output is address 5. So say you want to take the user input you read from address 4, and if you want to write to the user output or the display, you write to address 5. Addresses 6 to 15 are regular memory that can be used for anything and are not hardwired to specific components of the computer. So now that the boring part is out of the way, you can actually start programming the computer. Let's just spawn in a new programming card. We're not going to insert it yet, it's way easier to program without the programming card being inserted. First of all, we're just going to make a simple program to add two numbers together. So these numbers are going to be coming from the inputs over here. To do that, to add two numbers together, again we will need to write to address 0 and to address 1. So we're going to write to address 0, which is the input, first input of the addition. We're going to write there whatever is in the RAM address of the input. The input is going to be 0101. Wait, no. See, this is why you actually make screenshots and hang them somewhere so you can actually remember shit. Of course, you now need to also write to address 1. We're going to again take an input, and this will, the computer will make sure on its own that's actually going to get two different inputs. You don't need to worry about that. Of course, we also need to get the output of the addition. We need to put that on the output screen. So to be able to do that, we need to get the output. Right, so we get the output by reading from address number 2, and we write to the output. So in theory, this little program should allow me to add two numbers together and put it into the output. This program is the hello world of this computer. So we turn the computer on. It's going to ask me for input. For demonstration, we're just going to add 5 on 3. So 5 is already in there, so we're just going to press the green button. Now we enter the number 3. And there it is, the result 8. But the computer, of course, is just going to continue because nobody said it should stop. And we didn't enter anything there, so it's just going to think, well, this is right to address 0, value 0. So as you can see, it simply resets the first bit of the ALU, and it's doing that continuously. And the spot guns aren't firing because the switches are already in the correct position. But we don't want this to happen. Instead, we might actually want to add another number. So we want to put this in a loop, right? So that there will always be the next number. To be able to do this, we need to go back to the first instruction, right? So to edit the program counter, or the counter which indicates at which line of code the computer is executing, to write to address 3, we're going to write a constant value, and the constant value is going to be 1. So it's also going to, so when it reaches this line of code, it's going to be writing 1 to the program counter or line counter, and this will put it back at the beginning of the program. So now we can just insert the program again, then just quickly turn off the computer and turn it on again. So now we're just going to add 5 and 5. Just press this button again to add 5 again. So now we get the output, and so this here is this is the bit for 1 on itself. Bit for 2 is on, so you're going to remember 2. The bit for 4 is off, and the bit for 8 is on. So the answer is 8 plus 2, which is 10. 5 plus 5 is 10. The great thing is that, as you can see, it's asking for another input again. The program has actually gone back to the beginning. Let me just quickly add 5 on 3 again. Oh, we glitched it out. It still worked. No, it didn't. Let me just try that again. We're going to add 3. And then I'm just going to add 5. As you can see, it's just going to go through the instructions. When it meets that instruction, it's going to execute it to go back to the beginning. Now, of course, we're going to make a slightly more complicated program. We are going to be making a small counter. Right, so what the counter needs to do is the counter is going to be simply incrementing this thing here. So to be able to do that, we need to make sure that the ALU0 is going to be 0 again, reset to 0, such that it actually starts counting at 0, of course. So to do that, we just write to address 0, the actual value, not the ROM address, 0. So we just can leave that line as it is. The address 1, however, we want to add the value 1, such that it will always be incrementing with 1. Of course, it won't increment until we actually tell it to. So, to do that, we are actually going to make sure that address 0 is going to be whatever is in the ROM address of the output of the ALU. Right, so if we run this, it's going to be make ALU A be 0, ALU B is going to be 1, and next is going to be 0 plus 1 is 1. So ALU A is going to be set to equal to the output, which is 1. I'm just going to be adding 1 plus 1, which is 2, so it has incremented. Of course, we want to put this inside of a loop. So again, we're going to be writing to address 3, and we're going to write the value of this one here. If we go back to the entire beginning, it's actually going to start at 0 again, which is something we don't want. So, actually know what line this is. We can just look at this here, and you see that it's from right to left 0, 1. And it's going to be the value. So when we insert this, I think we need to restart the computer. Finally, it's a glitchy thing. So if this thing actually worked, value 0 should be incrementing slowly. So as you can see, it just turns to 2. Now it's 3. And now it's 4. So it's incrementing, but then that's great. We actually want to see it in the output. So we're just going to take you out and quickly erase the line. You can just erase it. The computer itself doesn't actually look at the colors, but because they're handy for actually knowing what we are writing, you can just paint them back. It's technically it is unnecessary. The computer can understand it without the colors. It's just checking for the white pixels. But for us humans, it's just very handy like this. So we remove that line, because of course the jump instruction needs to move forward. So we are going to be why does it need to move forward? Because of course we need to first make sure that it actually outputs stuff. So we're going to write to the output whatever a value is in the RAM address of the input, because it has already incremented the counter. So if we're going to check the output of the ALU, it's actually another incrementation that it's looking forward to. So we're not going to be doing that. We're just going to reading from the ALU inputs. As shown in the previous table, the ALU inputs are actually both actually also readable. You can't only write to them. So that's nice. So now we can just wait. We forgot to actually re-enter go back to the start instruction. So again, so it's going to be write to address 3, the simple value. The first line that isn't a reset is actually at line 2. So now that we've done that, just turn off the computer, turn it on. So in theory, it should now be writing on like soon. Yes. Then I should go back to the start. Now it's adding some numbers again. Now there's 2. Now there's 3. Now there's 4. So this program is working. But I'm not going to end this tutorial yet, because I still have to introduce you to if statements. So if statement, we can, for example, make the counter stop at a certain position. So again, we're just gonna delete this jump instruction because we need to move it forward a bit. So it has just incremented the counter. So to be able to check again, we need to, let me just think about it. So we want to make the computer stop at when it, for example, has counted to 3. Let's do 3. That's high enough. Let's demonstrate that the counter has actually been counting, low enough that we don't have to wait an eternity. So to be able to check if it's more or less than 3, we need to compare it to something. So the value of the counter is actually already in ALU A. So we are just, instead of the 1, which is for incrementing, we're just gonna write a 5 in there. So on ALU B, we're gonna write the value 3. That's when comparing to this 3 here. But in the next line is going to be a if statement. So we want to check if A, so the actual counting, is actually still less than. So for A is less than B, we need to paint this thing here white. One way to remember this is to simply say that A is on the left and B is on the right in simple alphabetical order. It's English writing order. And just want to paint the side white of the side that is more. And if you want to do equal to, just paint both of them. So if it's still less than, we're gonna jump back to the beginning. On the beginning, still line 2. At the beginning, it's actually going to make sure that B is 1 again, so it doesn't cause any problem. And of course, if it's done with counting, it has actually been passing this, and because you don't want the computer to actually start running this code of nothingness again, we are simply going to be putting the computer in a eternal loop. So what we're going to be doing is we're going to be jump to, and then we're going to make a jump to the line it's already on. So in this case it's going to be 0111, which is 7. So that should cause us to go into a eternal loop that's run forever. It's a sort simple loop that doesn't do anything. Let me just turn it off, turn it on, turn it off, turn it on, and I'm just gonna wait and hope that it works. Right, so we've started counting and we're now at 1. We're now at 2. Now it's 3. And now it has entered the loop forever. It worked! Yeah, I'm now very happy, I think. Okay, it worked first time. Did you expect that? Don't expect everything to work first time. That's why I'm telling you to experiment with this thing here, because you can actually see what the computer is actually doing. As you can see, currently this here, the A is no longer less than B. So the statement is false. You can also see that over here. Actually, the statement used to be false, so this thing here has been flashing on while that instruction was going. And it's now in this eternal loop. You can see that because it's writing with this thing here. So now that we finished the tutorial, you should be able to know how to program the computer. If you still have any questions or problems with programming, go to my Discord server. I am there, there's other people there who will be very happy to help you out with any problems with my programming my computer or other scrap mechanic logic creations or anything with logic on scrap mechanic. Go to my Discord server, go watch the original video of the computer. It's a very terrible video, it's my first video on YouTube. That's by far the most popular video on my channel. So yeah, I'll also all the blueprint files for both versions of the computer, for the programming lines, for some example programs will be found in the description. And if you made a nice program, share it in the comments, share it on the Discord server, and I might actually make a short showcase of it if it's a very nice program. Anyway, that's it for today. You have gone through over 23 minutes of boring nerdy shit, and you now should be able to do some more fun nerdy shit on your own. Have a nice day. Bye.